There is no single magic 50-cent mineral that you can pour into any dirty water and safely drink 10 minutes later, but there are real low-cost water treatment powders and minerals that come surprisingly close to that promise when used correctly and with limits. In villages where clear, safe water is a daily uncertainty, a woman bends over a plastic bucket the color of old bone. The water inside is brown, thick with dust, algae, and invisible threats that have shaped the health of her family for generations. From a small torn sachet, she pours a pale powder into the swirling murk and stirs. Within minutes, the water begins to change. Particles clump and sink, forming a dark sludge at the bottom. The liquid above turns gradually clearer, almost transparent, like a veil lifting from a landscape. To an outsider, it looks like a miracle, a few cents worth of mineral dust transforming dirty water into something that could save a child's life. The story behind that transformation is more complex and more human than any viral headline. It's a story of chemistry, public health, corporate engineering, and centuries-old traditional knowledge converging on one urgent question. How do you make unsafe water drinkable, fast, cheap, and reliably enough to trust with your life? Every year, millions of people still drink water contaminated with pathogens, heavy metals, and organic pollutants, not because they do not know the risks, but because they have no alternative. Diarrheal diseases linked to unsafe water remain a major cause of child mortality, especially in low-income regions where large treatment plants and complex infrastructure are absent. For these families, any method that promises clean water in minutes for less than the cost of a piece of bread is not a curiosity. It is a potential lifeline. The phrase, "pour this 50 cents mineral into any dirty water, drink it 10 minutes later," sounds like a modern water miracle. In reality, what exists today is not a single magic mineral, but a family of tools: flocculant-disinfectant powders, mineral salts, and natural coagulants that can mimic, on a tiny scale, what a full water treatment plant does. They bind particles, pull them out of suspension, and in some cases disinfect, bringing the water closer to drinkable. One of the most studied examples is a product developed by a multinational corporation in partnership with health agencies, a small sachet of powder known generically as a flocculant disinfectant. Inside there is no exotic secret element. The mix usually includes ferric sulfate, a mineral-based coagulant, and calcium hypochlorite, a chlorine-based disinfectant. At large scale, these are the same categories of chemicals used in municipal treatment plants. In a household sachet, they are pre-measured so that anyone can tear open the packet, stir it into a bucket of water, wait, and then pour off something much clearer and safer. At first glance, this seems to match the viral claim almost perfectly. For just a few cents a sachet, often less than $0.50, people in remote communities can dramatically reduce the turbidity of their water, strip out many pathogens, and walk away with something that is, by lab standards, much safer to drink. In many pilot programs, these sachets have been distributed widely in countries where floods, broken infrastructure, or chronic contamination make clean water scarce. Public health teams have documented reductions in diarrheal disease when families adopt such treatments consistently. But even here, the reality is more cautious than the headline. The powder does not work on every contaminant at every concentration, and it does not always make water safe in 10 minutes flat. The treatment process usually involves stirring, waiting for flocks to form and settle, filtering the clarified water through a cloth, and then allowing the disinfectant contact time to inactivate remaining microbes. That contact time can be on the order of 20 to 30 minutes, sometimes longer, to reach the safety levels demonstrated in studies. 10 minutes might be enough for the first visible change, but invisibly, the chemistry is still working. The mineral in these powders, often an iron salt like ferric sulfate or aluminum salts in other systems, is a flocculant. Flocculants neutralize the electrical charges that keep tiny particles suspended, causing them to clump together and sink. In a transparent glass, this process looks like dust gathering itself into soft, falling snow. Along with clay and organic debris, many bacteria and protozoa hitchhike into those clumps and are physically removed from the water as they sink. In university labs and field trials, scientists test similar mineral-based and plant-based flocculants using jar tests, where multiple samples of the same dirty water are treated under different conditions. They measure turbidity, count bacteria, and optimize how much powder is needed to achieve the best clarity and safety. Some studies explore natural alternatives, powders from seeds such as morina or guar gum, or combinations of mineral salts and biodegradable polymers. The goal is to create something cheap enough for rural families and robust enough to work in a wide range of water sources. Researchers evaluating natural flocculants have shown that properly formulated powders can significantly reduce turbidity, heavy metals, and organic contaminants, offering eco-friendly options for small-scale water treatment. These powders may not look different from the $0.50 mineral of online lore. A small packet of fine grains tipped into a bucket on a hot day. In some communities, local organizations experiment with such formulations, aiming to reduce dependence on imported products and to tailor treatment to local water types. Yet the promise of any dirty water hides a dangerous simplification. Water contamination is not just about visible dirt. Some of the most serious threats are invisible: arsenic, nitrates, industrial chemicals, and dissolved metals that flocculants may not fully remove. A powder that works beautifully on muddy river water may be far less effective against clear but arsenic-laden well water. A villager looking into a freshly cleared bucket might see purity where chemistry sees only partial protection. Experts who study drinking water repeatedly emphasize that there is no single treatment that can take out all of the bad contaminants and leave only the good stuff. Methods that remove bacteria might not remove chemical pollutants. Treatments that strip out nearly everything, such as reverse osmosis, also strip out beneficial minerals and require complex installations. The appeal of a selective miracle mineral, one that knows which molecules to catch and which to let pass, is powerful, but current science does not yet offer that in a cheap, universal, 10-minute form. In some articles and consumer discussions, people are warned specifically about products claiming to remove every harmful contaminant while preserving healthy minerals, because such selectivity is not how real purification technologies work. When a filter or powder claims to leave the good stuff, it often means it leaves most of everything, including some undesirable compounds. True safety still depends on understanding the specific water source and matching it to an appropriate treatment. The powder sachet solutions, when used as instructed, are an honest attempt to give households some of the power of a full treatment plant in a handful of dust. They are designed following the multiple barrier concept. First, coagulation and flocculation to remove particles and many microbes, then disinfection to kill what remains. For emergency situations, floods, outbreaks, displacement, such sachets have proven to be a valuable tool. They do not turn sewage into spring water, but they can turn marginal water into something much less likely to make a child sick. Parallel to these lab-engineered products, another narrative runs through villages and small towns: the use of natural seeds and clays as coagulants. In field studies in developing regions, scientists have tested morina seed powder and other plant-derived flocculants to see whether traditional practices can be standardized and improved. These experiments show that local, low-cost materials can, in some cases, rival industrial chemicals in reducing turbidity in certain metals. Though they may lack the built-in disinfectant of some commercial powders, they point toward a future where communities could produce their own treatment agents from nearby fields and trees. The image of a 50-cent miracle mineral, then, becomes a metaphor. It stands for a range of technologies, chemical, natural, and hybrid, that aim to compress an entire water plant into a process that fits into daily life. A sachet in a kitchen, a scoop of powder beside a river. What's real is the chemistry of flocculation and disinfection. What is dangerous is the illusion that a single act, a single packet, can erase every risk in every water source. Claims like, pour it into any dirty water and drink it 10 minutes later, spread fast online. They play to a deep human desire for simple fixes in a complex world. Health professionals and water engineers, however, approach such statements with skepticism, because they know how varied water contamination can be. They also know how much work goes into testing and verifying that a given method works under specific conditions. In critical reviews of water myths and scams, specialists point out that some products oversell their capabilities, promising purity based on vague ideas like energizing or structuring water, or using mineral stones in a way that has no credible scientific backing. These are not the same as the rigorously tested flocculant-disinfectant sachets, but in the public imagination they often blend together into a single category: magic minerals that turn filth into safety. Part of the educational challenge is to separate science from salesmanship. The reality on the ground is full of nuance. A family using a tested, approved powder in reasonably clear surface water, following instructions and waiting the recommended contact time, can reduce their exposure to pathogens dramatically. That same powder, poured casually into heavily industrial wastewater, might barely scratch the surface of the risk. Without education about what the treatment does, and what it does not do, people can gain confidence faster than they gain safety. So how should one see the promise of a 50-cent mineral? As a powerful tool, but only one piece of a larger puzzle. Water safety depends on understanding the source, applying an appropriate treatment, and, where possible, testing the results. In some contexts, that treatment might indeed be a mineral-based powder, used daily and carefully. In others, it will be filtration, boiling, or more advanced technologies. For communities, the deeper value of these powders is not just that they are cheap. It is that they can be used at the household level, by people who cannot wait for a distant utility to fix a broken pipe or upgrade a plant. They represent a shift from centralized control to distributed resilience. Each bucket becomes a miniature treatment station, each family a participant in their own protection. Behind every sachet is a web of research, policy, and collaboration. Public health agencies evaluate performance, NGOs coordinate distribution, and local educators train families on correct use. Scientists refine formulations to improve effectiveness against wider ranges of contaminants while keeping costs low. And at the edge of this system, marketers and influencers shape public perception, sometimes responsibly, sometimes not. The tension between scientific nuance and marketing simplicity is especially sharp when the stakes are potable water. On one side, rigorous documents explain contact times, dosage, limitations, and the importance of follow-up filtration. On the other, a headline promises instant transformation in 10 minutes for any water, anywhere. Between these two poles sits the everyday user, trying to decide whether to trust the clear water in a plastic bucket. When people first see the transformation, a murky liquid becoming clear, they often experience a moment of awe. It feels like watching pollution physically fall out of existence. For educators, that moment is an opportunity to explain how flocculation and disinfection work, how different contaminants behave, and why waiting, filtering, and sometimes combining methods matter. Instead of a miracle, it becomes a lesson in empowered, informed self-protection. In this sense, the most important mineral poured into dirty water may not be ferric sulfate, aluminum salt, or seed powder. It may be knowledge. Knowledge that clarity is not the same as purity. Knowledge that no packet, no matter how cleverly designed, replaces the need to understand what you are drinking and why. The woman at the bucket, watching the sludge settle and the water clear, is not asking for magic. She is asking for a fair chance at health for herself and her children. If a powder that costs less than a coin can bring her closer to that goal, and if it is used wisely, it is a technology worth celebrating, cautiously, honestly, and without exaggeration. The real story is not about miracle minerals. It is about how science, when stripped of hype and placed gently in people's hands, can turn risk into resilience, one bucket at a time.